Hey, welcome back. Hope you enjoyed the first presentation on prior knowledge. Fairly challenging, some of that stuff, if you haven't seen it before, so you might have to go back and have a look again. This time what we're doing is having a look at revision topics part 1 and part 2, two more presentations here, and these are the topics that we feel probably pretty confident with, but really want to make sure. And so you will have seen a lot of this stuff before, I think. Let's check it out. The first section here is, as you can see, properties of real numbers, and I think mostly you would be familiar with these things. Let's have a look now. The commutative property here is you can add things up in either order. So it doesn't matter if you have 2x cubed plus y, that'll be the same as y plus 2x cubed. 2 plus 3, same as 3 plus 2. So that idea isn't too bad. And of course, multiplication works the same way. The commutative property, if you multiply A by B, it's the same as B by A. 3 by 2 equals 2 by 3. And so any algebraic terms put in different order will give the same answer. So that's called the commutative rule, where the order in which you do the operation doesn't matter. The associative property, coming down here now, the associative property, again, is how you associate, if you like, the terms. So you could add up A and B and then add C, or you could add A to the result of adding B and C first, doing the brackets first there. So with addition, it doesn't matter about that, the association of terms. So the associative rule holds. The associative property of multiplication, as you might guess, also does. If you multiply A by B and then multiply the result by C, it's the same as multiplying B by C and then multiplying the result by A. So again, having a look at the algebra here of these terms. The dot there means multiply, often used as a multiplication symbol instead of the cross. So here this means multiplication. So perhaps give that one a tick. Just making you familiar with what you can do with terms in this course, arranging them and what order you might have to work in. The distributive property is how the operation is distributed, if you like, over addition or subtraction. So here multiplication is distributive over addition here. So what it means is we can either add up B and C first and then multiply by A, or we can multiply A by B and then add A by C. So that product, that multiplication of A by B plus C, the multiplication is distributive over addition. You can distribute it, A by B plus A by C. And so we often call this expansion of brackets, or multiplying brackets out, or expanding terms, etc. Okay, these down here, the identities, the additive identity means what element or number can you add to any term to leave it unchanged. So the key word here is identity. An additive identity is that element, here it would be 0, such that when you add it to A remains unchanged. So we understand that that's what 0 is usually. And also if we have 0 plus A, it would also be A. The multiplicative identity, is there some term that you multiply by to leave the element unchanged? Well, of course it's 1. If you multiply any number by 1, then that number is left unchanged. So here, just looking at it, in this one here, 1 times 2/3 can be thought of as 4 over 4 times 2/3, or 8 over 12. And so it leaves it unchanged, if you like. The additive inverse. The additive inverse. Now the inverse is a property of sets the IB expects you to know, the inverse is that element which, when you add it to the given number, produces 0. So what is it? It'll be the negative, won't it? A plus its negative gives 0. So neg A is called the additive inverse. So 6y squared, if you add neg 6y squared, you get 0. So it reverses, if you like, the value of the number, makes it 0. Multiplicative inverse. Okay, so here, multiplicative inverse is to produce the identity back again, 1. So in other words, A times 1 on A produces the identity. So the idea of the inverse is to produce the identity back again. Okay, so here, if you had y take 3, you would have 1 on y take 3, and multiplied together gives the multiplicative identity 1. If you like, it reverses the effect of that number in one sense like that. Okay, well, not too much. There's some terms again. The IB expects you to know these terms. That's more so the language and the notation and the terminology here rather than the mathematics. It might be a bit new to you. So let's go to the next section that I said before in that first presentation under prior knowledge. You might actually have some questions about. And that was the section on roots and radicals and surds. So I've made a little section here for you. Roots and radicals. And this form, when you're working with this sign, and you would be familiar with it, that sign there is sometimes called the surd form, where you have a number written with a square root sign or the radical sign. So this is called the radical sign, and it's used for designating roots of numbers. Now, what is the root of a number? Well, let's do the square root. So the square root of 4 is 2. Most people know that. Why is that so? Well, the square root, so we're doing this one first, square root implies the number which multiplied by itself gives the original. That's a very simple explanation. So in other words, the root of 4 is that number which multiplied by itself will give that number 4. So it's obviously here 2. What about other roots? What about something like the cube root of 27? The cube root. Well, you might realise there it's the number which cubed. Number cubed to give the original. To give the original value that we're taking the root of. So here what would it be? The cube root of 27 would be 3. Because 3 cubed, 3 by 3 by 3 is 27. So you could actually have anything, any root of a number. What about the nth root? Let's look at that. What does that mean? The nth root of x would mean the nth root would imply the number which raised to the n, to the nth power, gives x. That's what that symbol might mean, gives the value x. So that's important. Sometimes it's important to realise that this symbol we're going to mean for root of 4, it means the positive root only. So it's often called the principal positive root only. So it's 2, not neg 2, because neg 2 by neg 2 will also give itself. So the principal square root is the positive one, because obviously here, if you look at these definitions, when you have back up here, a number which multiplied by itself gives the original, that could have been -2 by -2 also. But we're looking with the radical sign, meaning the positive root only, called, if you like, the principal root of the number. Principal root of the number. Obviously, you can find things like the cube root of, what could we have, -8. Well, there is only one answer there, and that is -2, because a negative times a negative times a negative would give -8. So there, that has only one, and that would be -2. All right, so is there anything else we might do? We could do, I know, the fourth root of 16. What number raised to the fourth power gives 16? Then the answer is 2. Now, this is called the principal root because there is also another number which multiplied by itself 4 times, or raised to the fourth rather, gives 16. That's -2. So we only talk about the positive value here when we use the radical sign. So just think, if you had this problem, x to the fourth equals 16, an equation, there would be 2 answers. Plus or minus 2 would be included there. But there are actually 2 numbers which raised to the fourth give 16. So please note, when we use the radical sign, we are looking at the positive root only. So the fourth root of 16 is only written as 2. Okay, so that gives you a little bit of an idea. Sometimes, however, coming down here now, let's go down. Sometimes, however, you can't work out that root. Here's a couple of examples where we use the radical sign. And again, we're being reminded here that an expression involving the radical sign is called a surd. Usually we'll try and work it out. But can we always? Let's have a look at these 2 right-angled triangles. Let's look at this one here for a start. Here, by Pythagoras, we can say the square on the hypotenuse equals the sum of the squares on the other 2 sides. So x squared is equal to 25. So here, to find x, we'll find the root of 25, which is 5. Oh, but hang on, it is also -5, isn't it? The square root of 25. And we don't include this here because x is a positive. That is, x must be greater than 0. Why? Because it is a length here. So we only put in the one solution. I like to put in brackets myself. X is greater than 0 at this line here, explaining that we know there is another square root of 25, it's -5, but we're saying in this problem, x can only be a positive value because it's an actual length of a side of a triangle. What about this one over here? So we've worked that one out exactly to 5. Here Pythagoras says the square on the hypotenuse equals the sum of the squares on the other 2 sides. Okay, so here we go, 16 and 64, y squared is 80, looks pretty good. Let's take the root of both sides, so y is the root of 80, and again it's a positive root. Y is going to be greater than 0 because it's a distance or a length. Now what have we got? We can't work out the square root of 80. It's not a perfect square, is it? So to actually keep this as an exact number, we have to leave it in the square root form, or leave it with the radical sign. So this is called surd form, and it's the only accurate way of representing square root of 80, because if you work that out as a decimal, it would keep going. It's a non-terminating, non-recurring decimal, and from the prior knowledge in the first presentation, we know that you can't actually write that as a rational number. It's irrational, and therefore the only accurate way of representing it is in surd form, or with that root sign. If you start trying to work it out in decimals, you're going to have to stop somewhere, aren't you? It's an infinite decimal. So when you stop, you now have introduced some inaccuracies. Right? You have actually not represented the square root of 80 exactly, because it is an irrational number. Okay, so what that means is if we want to work precisely in mathematics with this is an irrational number, then we want to keep it in that form. So this leads us to some problems, doesn't it? It means when we don't want to approximate it, we want to keep it exact, so we've got to keep the root sign in it. Well, hang on. How do you work with numbers with root signs? That's a good question. And guess what? Come down here. We've got some answers here. Oh, here we are. Simplifying radicals, or working in surd form, aka, so we'll put over here, aka, working with surds. Please keep in mind, young mathematicians, that why are we working with surds? Because we want the exact form for an irrational number. If you use a decimal, you're going to have to truncate it, round it off at some stage, and therefore it isn't any longer the exact mathematical form. Okay, so let's have a look at some surd rules here. So we're talking about having two positive numbers that we're finding the root of, the nth root of a times the nth root of b. This first rule says you can multiply a and b together and then get the nth root afterwards. So you don't have to find the two separate roots, you can put them under the one root sign. And similarly here, the nth root of a root of a over the same root of b, you could do a over b first and then find the root of that. And you can go both ways. Okay, so here you can go both ways. Each rule can be applied in either direction. So let's do some. Root of 5 by root of 5, we can say 5 by 5 is 25, which is 5. Please note, in this textbook, Pearson's new textbook for the new course, that dot between the 5 is being used as multiplication sign. That's quite often done. So here, see what we're doing? A root by a root is the root of the product. You don't actually have to find the root of 5. So root of 5 by root of 5 is root of 5 by 5. Let's do another one, and that's a special case I mentioned here, because you're actually multiplying a root by itself. Oh, by definition of the square root, if you multiply it by itself, you should get that number back again, and yes, it works. We're doing it here to apply that new rule. Let's do the new rule again. The root of 2 by the root of 8, well, you can multiply them together first. 2 by 18, sorry. 2 by 18, root of 36 is 6. So can you see that working in surd form may allow you to come through and work out the exact rational answer, even though the numbers you're working with were irrational. So that's the value, that we would never to convert those to decimals. Keep it in exact form, using surds, using radical signs, and as we come through, we find the answer to our problem is an exact rational number. So here we are, root 48 on root 3. Let's do the 48 on 3 first. We get 16, and the root of 16 is 4. So working with surds, are you getting the hang of it? The cube root of 6 by the cube root of 36. You can take the cube root of the whole thing. Cube root of 216 is 6. Please note, come up here again, working with surds. Why? This is the exact form for an irrational number. Form because the numbers are irrational here. And we work in the exact form, and if we're lucky, as we have been here, we find at the end it comes out to a nice rational answer anyway. Have you got that rule? Because I'm going to ask you to do some problems in a minute and just check this out. Let's come down to some more now. Okay, what about just working with a surd form with a radical root 24 up here? What can we do We don't want to go to decimal, remember, because it's a infinitely long decimal. We don't want to truncate it, it's approximating it. Can we get a better grasp on 24 though? Yeah, well, we could call 24 4 by 6. So we're going to come back the other way this time and call it root 4 by root 6. As we said, do you remember? We're going to have to go back now. Do you remember? We can apply the rule in either direction. So that's what we're doing. We're now breaking down a radical into a product. And was there any point? Yes, because the root of 4 can be simplified as 2. So that was a value. Just notice what Pearson's are saying here. The root of 24 as 3 times 8 is not beneficial because you can't find the root of either of these two. So that's a dead-end street. You don't get anywhere. What are we aiming to do here? We're aiming to take a surd, keep it as exact form, but simplify it in some way where we don't use the exactness. Simplify to get a better understanding. So root 24 is better understood as 2 root 6. Getting down to smaller terms there. So let's express some of these. The root of 18. What will you try to do? I will try to write 18 as the product of 9 by 2 because 9 is a perfect square. Using our rule, root 9 is 3. So it becomes a simpler, more easily understood exact form. So if we go to root 80 down here, what would you do? Well, you could call it 2 times 40. No. That's not going to help us much. But we would like to have the biggest perfect square in there. 16 times 5 is root 16. There's our winner because that's a perfect square. So this is 4 root 5. Here they have it nicely stated. 16 is the largest factor that is a perfect square. And that's the idea. Because we're trying to come back up the top here now, working with surds, the exact form for this irrational number. And we're trying to simplify it, get a better understanding, break it down if you like. So let's do this one. Root of 3 over 25. So here you can call that the root of 3 on the root of 25, which is root 3 on 5. It was profitable using the rule here because in the denominator we had a perfect square. What about the last one now, the root of 1,000? The root of 1,000, well, you know 1,000 is not a perfect square, but 100 times 10 is profitable because the root of 100 you can work out. 100 is a perfect square. Are you getting the hang of it? What are we doing here? We're trying to investigate in more depth some of the symbols and notation and basic rules that we have done up to this course. The ideas behind the square root sign, the actual behaviour of numbers. It's trying to give a good grounding in that. Okay, so let's come down a bit. And I think this is our last one, and then I'll let you loose on some problems and see what you think. Now, obviously, Pearson said here, we prefer not to have radicals in the denominator of a fraction. Why? Well, let's have a look. 3 over root 2. Well, that's hard to understand how big that would be. I'm dividing 3 into root 2 parts. Root 2 is not an exact, well, it is an exact form, but it's an irrational number. How many parts would that be? That's hard to actually understand, and we would like to try and simplify this so we don't have division by this irrational number. That's the idea of it. So here, therefore, what we could do is to use this rule, the root of a by the root of a is a. So let's play with that. 2 on root 3. There's the trick there. If we multiply top and bottom, that's numerator and denominator, by this root 3, look at what happens in the bottom line. Root 3 by root 3 is 3. Remember that now. The root of a number times itself gives the number back again. That's the definition. Here it is up here. Root a by root a is a. And so this is a bit more easily understood. 2 root 3 on 3. We've got 2 lots of root 3. We're dividing up into 3 equal parts, if you like. What about this creature here? It looks a bit different, But what we're going to focus on is getting a whole number in the denominator. So it's divided by a whole number, a rational number, not a radical. So what will we do? All we have to focus on is the denominator has root 10. So we will multiply top and bottom by root 10. Root 7 by root 10 is root 70, and root 10 by root 10, let's check that down here, root 10 by root 10 is 10. So this is root 70 over 4 times 10, or root 70 over 40. So that's quite nice. Okay, now you might like to pause the presentation, maybe go back and check some of those rules again. Look at it in your book if you've got your book there. And now what I want you to do is to come down here and let's have a look at the problems. There are 19 problems here, and they each involve some of those rules. How to work with this third form, or the radical sign, remembering we want to keep the answer exact mathematically. We don't want to go to the decimal form of the irrational number and round it off. We're going to lose accuracy that way. So here we go, we've got 19 problems. Now, I've done something different in this presentation. Thanks to Pearson's, they have published complete solutions, not just answers. So some of you may have had trouble in that first presentation getting the answer, and it wasn't shown in full form, only the answer was shown. Here, look at what they've done. This is the fully worked solution, not just the answer on the end, but how you think of it to go there. So I'm just going to scroll down here so that when you want to come to the answers, you can go back and freeze it and check your answers, because I really strongly recommend that you, as you do a few problems, go and check it so you're on track. Don't do a whole lot and get them all wrong. Okay, so here we are, here they are. So I'll just scroll there, that when you want to mark it, you can come to any point and pause the presentation and mark your work. Okay, so we'll go back up to the problems now, and you might like to pause the presentation there, have a go, write down the first 3 or 4 or 5, and then rewind the presentation back to that solution set. Well, we're making progress. It's very good to see what we're doing, though. We're trying to go back to basic understanding of our tools, and our tools in mathematics, of course, are the numbers and the various forms of the numbers. So this is where we're starting this IB course. So have a look at it, see what you think, and keep going back over it. You can read the textbook also. That's another good way of mastering this. Now, I'll leave you with that. I've got one more for you, revision topics part 2, where we go over some of the other things in that prior knowledge that the IB brought out that may be a little bit rusty or not covered that well in Australian schools up to the end of year 10. Anyway, for at the moment, it's cheers from me, and I hope to catch you again in that next presentation.